Halliday Resnick Krane Volume 2. In this video lecture, I will discuss MCQ solution related to chapter number 30, that is about capacitor. So let's begin. Question number 1 is, two parallel metal plates that have charges Q1 and Q2. Is this an example of capacitor? Option A is yes. Option B is only if Q1 is equal to minus of Q2. Option C is only if the signs of two charges are different. And option D is no. So for a capacitor to exist, there should be two metal plates and it would be separated from each other through a distance. So it doesn't matter the imbalance of charges. So option A is the correct option. Question number 2 is, the centers of two identical conducting spheres of radius r are separated by a distance that is greater than 2r, like the distance double of their radius. A charge plus q is on the one sphere and a charge of minus q is on the other. The capacitance of the system is C0. Additional charge is now transferred so that the charge on each sphere is double. So what is the new capacitance now that the charges have changed? It's 4 of original capacitance, or 2 times of original capacitance, or this is equal to the original capacitance, or it could be the 1 by 2 of the original capacitance, or this information is not enough to give answers. So now we have these two spheres that are having a radius r and they are separated through each other with a distance t that is greater than 2r. So we have to discuss that what is new capacitance when the additional charge is transferred. As we know that the capacitance is actually theoretical factor, so it depends upon the dielectric inside the capacitor as well as the shape, size and area of the capacitor, but not on the charges or potential difference. So option C is the correct option. Next part is, what is the new potential difference between the spheres? It's 4q by c0, 2q by c0, or q by c0, or q by 2c0, or not enough information to give the answer. So here we know that the charge initially was q, but now the new charge is doubled, like 2q. So by definition we know that q is equal to c delta v. So if we see here the potential delta v, this is equal to q by c. Now charge would be 2q by c. So option B is the correct option. Question number 3 is, the center of two identical conducting spheres of radius r is separated by a distance that is greater than 2r, like this. How does the capacitance of the system changes if the separation of two spheres is decreased? Capacitance increases, capacitance decreases, or capacitance remains the same, or this information is not enough to give answer. So here we know that capacitors are although spherical, but these are separated through a distance. These are not inside each other. So here we will use a formula like this: C is equal to A epsilon naught by D. So A is the area of the capacitor and D is the distance between the metal plates. So now as the separation is decreases, so capacitance increases, as the capacitance is having the inverse relation with the separation. So option A is the correct option. Question number 3 part B is, how does the capacitance of this system changes if R is decreased? Capacitance increases, capacitance decreases, or it remains the same, or not enough information to give the answer. As we know that the capacitance is equal to area into epsilon naught by D. So area would be, for this spherical shape, is pi r square. So here we can see that if R is decreases, then the capacitance will be decreases. Option B is the correct option. Next question is, which of the following changes to an ideal parallel plate capacitor connected to an ideal battery will result in an increase in the charge on the capacitor? Decreasing the potential difference across the plates, or decreasing the area of the plates, or decreasing the separation of the plates, or none of. Okay, so now here if we see that the charges actually depend upon the capacitance as well as the voltage. So for the charge store depends upon the applied potential, as well as if we increase the ability of the capacitor to store more charge, then the charge could increase on the plates. So now if we see that capacitance is equal to A epsilon naught by D, so decreasing the separation can increase the capacitance. So the option C is the correct option. Next question is, equation 30.5 neglects fringing effects near the edge of the plates. Does this equation under or overestimate the capacitance of a real parallel plate capacitor? Option A is overestimate, option B is underestimate, and option C is neither. The expression is exact. So we have equation number 35, its capacitance is equal to A epsilon naught by D. That is neglecting the fringing effect. So first of all we have to know what is fringing effect. Fringing effect means that near edges electric field extended the area of the overlap so that the capacitance of the practical capacitor is much more greater than the calculated value. So here we are actually underestimating the value of capacitance through this equation. So option B is the correct option. Next question is question number 6. What is the capacitance of a single spherical conductor of radius r? This is equal to 4 pi epsilon naught into r. So option B is the correct option. Next MCQ is two capacitors C1 and C2 are connected in series. Assume that C1 is greater than less than C2. The equivalent capacitance of this arrangement is C. So where? Option A is this equivalent capacitance is less than C1 by 2, or C1 by 2 is less than C is less than C1, or C1 is less than C is less than C2, or C2 is less than C and this is less than 2 of C2, or 2C2 is less than C. When the capacitors are connected in series, then their equivalent relation would be 1 by C is equal to 1 by C1 plus 1 by C2. So here we know that C1 is less than C2. So in series combination, the equivalent capacitance is always less than the smallest capacitance of the circuit. So it means that the equivalent capacitance C would be even less than C1. So option B is the correct option, in which this capacitance is less than C1 and this equivalent capacitance is greater than C1 by 2. Question number 8 is two capacitors C1 and C2 are connected in parallel. Assume that C1 is less than C2. The equivalent capacitance of this arrangement is option A, C, equivalent capacitance is less than C1 by 2, or C1 by 2 is less than equivalent capacitance and this is less than C1, or C1 is less than equivalent capacitance is less than C2, or C2 is less than equivalent capacitance, that is less than 2 of C2, or 2C2 is less than equivalent capacitance. So here the combination is parallel, so the equivalent capacitance would be by adding simply all the capacitance in the circuit. So C is equal to C1 plus C2. So now the equivalent capacitance would be greater than even the most greatest capacitance of the circuit. So now here the option D is the exact option.